Hi, this is Mr. Yeager with physics again. We are looking at sound today. We're not going to go through this whole PowerPoint. We're going to try to go over what is sound in particular, the Doppler effect in great detail, and then some examples of the Doppler effect with bow waves and shock waves. We're going to stop there. We're going to stop before waves at a boundary. That may be a separate quick lecture video. All right. So by this point, we have gone over the properties of waves and the behaviors of waves. Now we're going to look specifically at sound itself. All right. And so sound itself is a longitudinal mechanical wave. All right, a longitudinal mechanical wave. So it does carry energy. It is a wave form, and it has to have a medium. Being a mechanical wave, it has to be able to travel through matter in some form. It cannot travel through a vacuum at all. Again, since it's longitudinal, we'll be talking about compressions and rarefactions if we ever try to draw it out. There are a lot of links in this PowerPoint. If you are interested in looking at any of these, basically go to the original PowerPoint itself and basically copy and paste. I think unfortunately a lot of the links at least don't work through the school itself, so it might be something that you have to do at home. Maybe I will link to it directly. All right. So that is sound. The next page, basically, if you want to look at this link, it just kind of shows you how the ear works. Again, how do we hear sound? Obviously, it causes some vibrations that basically vibrate the air around your ear, into your eardrum, and so forth. All right. All right, so that's what that will show you if you want to take a quick look at that YouTube video. With
John
frequency.
White, you need to
Sorry
return
about the
to your
announcement.
classroom. John White, you need to return to your classroom.
With sound, eventually you'll see that frequency is kind of the main factor that will manipulate how we hear sound. All right. So I mentioned I have this slide in here again mainly to kind of go, okay, don't forget about what frequency means. It's waves per second. All right. How to calculate it technically, doing these quick problems, 60 waves divided by 3 would be a frequency um, of 20 hertz. Man, did that slowly, but 20 hertz. All right. So frequency will be, you will see when we talk about pitch, when we talk about Doppler, when we talk about harmonics. All right. Frequency will come into play quite a bit. All right. Here's just something fun we do in class, a quick hearing test. Again, it'll help you show, it also shows you very clearly as frequency decreases, the change in sound itself. Okay. And so basically the next thing is, how does, again, we said sound needs a medium. It is a mechanical wave. All right, so it has to be able to travel through gas, liquid, or solid. All right, and so which of these would sound travel fastest through? Well, what we need to think about is, just like with any wave, the speed of the sound itself depends on those particles colliding one into another and transferring that energy. So it turns out that that sound will travel fastest through a solid. Solid has the fastest motion of sound because those particles are fixing very close together. Then it would be liquid, and gas is actually the slowest, which often students will tell me they think it'll travel fastest through a gas. I think what they are thinking about is they can understand the sound through gas better than through solid. Obviously, that vibration is something that our ears are not used to try to hear something through a solid. But because the particles are closest in the solid, they will travel fastest. Sound will not travel in a vacuum, and this YouTube video kind of shows a quick experiment. You have to move to like the 9-minute mark, but it'll show you basically an electric bell inside a glass container, and all the air is removed. You'll hear the sound decrease, decrease, decrease. It won't ever go away because it still vibrates to the table, but it will decrease a great amount, the volume of it, because there's less air particles to vibrate. All right. Now, it turns out the medium is not the only thing that will affect the speed of sound. Temperature will as well. And basically, the main thing here is as temperature increases, the speed of sound will increase. And again, that's because the particles will move faster. There is a formula for it, as you see at the bottom, but that is not a formula that needs to be known for AP Physics. It could possibly be something that's thrown on a free response, that you might have to use for your justification, but they will give that to you. All right, they will give it to you saying use this formula. Otherwise, you're very unlikely to actually see this formula used at all. But again, temperature will affect the velocity of sound in the air or through any object. All right, so that leads us to another very important concept of sound, and that is pitch. All right, this will be a common thing that will be questioned about what happens to the pitch. Describe the pitch. Explain why the pitch changes. Okay, and so pitch, the definition itself is the highness or lowness of the sound itself. Okay, it's the falsetto, the I'm going to go and do it sound versus low sound. The pitch changes. Basically, I've released different frequency vibrations from my voice. Okay, so pitch is directly related to frequency. All right, it turns out that if I want to increase the pitch, I increase the frequency of the wave itself. All right, and so there's going to be multiple ways we can manipulate with that. We're going to talk about doing, why you get a different pitch on a guitar as you move the hand position on your guitar. Obviously, getting a higher pitch maybe at the bottom versus when it's all the way at the very top of the whatever you call the end of the guitar. I'm not musically inclined. All right, so increase pitch, increase frequency. All right, what people get confused with this very quickly is they always want to talk about volume, the volume of the sound. All right, volume and pitch are not related, are not the same. They're not related either. All right, they are completely different quantities and characteristics of the sound. The only thing I'll tell you about volume is it does relate to the amplitude and the energy of the sound. Okay. All right, it's related to the amplitude. Okay, primarily this will be the main one to relate. I have seen questions where they have graphs of sound waves, and the ones with larger amplitude have higher volume. They could ask that, but they don't go hand in hand. You could have a very low volume, high pitched sound. You could have a very low volume, low pitched sound. Okay, they don't relate at all. All right, so be careful with that with volume. All right. Again, pitch is directly related to frequency. All right, we will eventually. This statement's a little misleading. All right, we will relate the speed of the wave through different tensions of string in a bit. But again, it's possible to obviously relate pitch to frequency and then frequency to wavelength. So obviously, if high pitch is high frequency, then it will have a low wavelength. But if they ever ask you a question of what will affect pitch, say frequency, not wavelength. Wavelength is basically something that changes as well due to frequency changing. Okay? So it's all about frequency. That's what I can keep on telling you over and over again. So this leads us to our last big topic for today, is the Doppler effect. All right? And you've all heard, this is the car, the ambulance zooming by you, the sound as it goes by. All right? And the Doppler effect, as it states right there, the Doppler effect is due to a change in frequency. A change in frequency. All right? So it's a change in pitch that's occurring. Sorry about coming back and forth here. A change in frequency, a change in pitch due to the motion of the source or the whatever's creating the sound. So the two key things about Doppler effect is it's a change in frequency due to motion. All right? You will not hear the Doppler effect if nothing is moving. There is no Doppler effect. All right? But once there is some sort of motion, we can create this Doppler effect, this apparent change in frequency, which again means a change in pitch that occurs. That's why as an object gets closer, we hear a higher pitch sound. While it goes away, that pitch decreases. It's sort of like that classic bomb falling sound, the sound, okay? Any of those basically going by, that is the Doppler effect, that change in frequency. Now, obviously we will hear a change in volume, all right? But volume is not related to the Doppler effect. It's just, again, it's a happenstance that it will usually obviously change because basically how close are you to that sound itself, all right? but it has nothing to do with the Doppler effect itself. All right? The faster the object moves, the greater you'll hear the Doppler effect. In other words, the greater the change in frequency will occur. It'll occur much more quickly. All right? The rate at which it changes will be much more quick. All right? So these are the types, down at the bottom right here, these are the types of drawings we need to be ready for. Not necessarily like the people themselves, but the circles, all right, around this police car. What's happening is, with the Doppler effect, is as that car is driving, it's releasing the sound. Well, the sound travels at a specific speed, but the car can either get faster or slower compared to the sound. And so what's happening here is, technically you could say, the car is chasing the sound that's creating, and so in front, that sound in front, all the waves of the sound, all the releasing of the sound is much closer together. And so what happens is, if all of these waves pass your ear very quickly, you're going to hear a high frequency, many waves in a small amount of time. While those behind the car, those waves are more spread out so that less waves are passing over time. Okay, I'll go say this, less waves over time. This is more waves over time. You can see what I'm trying to get across here. All right. This person over on the right will hear a high frequency, high pitched noise. The person on the left will hear a low pitched, low frequency noise. All right. Sorry, I needed to get that out of the way so you can read that a little bit better. All right. Now, there's many uses for Doppler effect. All right. We'll quickly talk about certain applications, but this is how radar guns work for police cars to capture a car's speed. Okay. It's basically with their radar gun, they send out multiple waves, and when they hit the car and bounce back, depending if the car is getting closer, each successive wave that was sent out should come back more quickly, and then they can measure the speed based on how quickly those waves are coming back, even if you're driving away. This right here would be an absolute must for you to check out and try to watch. This site goes over, it does a lot of very good examples, very visual examples of the Doppler effect. It shows a lot of math. Ignore all math. All right. We will not do any calculations for Doppler effect. There is a lot of equations we could use. There are no equations that AP Physics 1 asks you to use for the Doppler effect. It's all conceptual. You will have to notice, should the waves get closer together, should the waves get farther apart, or should the waves basically stay the same? Okay, is what we are looking at here. All right. So, what we have happening here, okay? This is, again, the pictures we have to notice, the ones at the bottom, all right? We have basically two situations. We have basically this cricket. Think of a cricket. We have the cricket standing in the middle. If it's standing perfectly still, it'll create these concentric circles of sound, all right? So basically what I'm trying to show here is this was the first chirp, this was the second chirp, third, fourth, fifth. And he's doing it in regular intervals, so a regular chirp, 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 chirp sound, okay? And if he's standing perfectly still, all of them should be equally distanced apart, which means person A and person B should hear the same pitch, the same sound, all right? There won't be any change in sound, all right? And we can basically then go, that cricket must not be moving, okay? That cricket must not be moving if both of us are hearing the sound exactly the same, all right? Same pitch and everything. Over on the right-hand side, now the cricket is moving. It's hopping toward person B while continuously making the chirping sound. What would happen is, again, technically, he's chasing his own sound, okay, in a way, that's kind of the way we're trying to look at it. And so person B, they'd be able to notice, hey, something is approaching me. They're hearing the frequency increase. More waves are hitting that person's ear over time than person A, who would interpret this as, hey, that cricket that I initially heard is leaving. It's going farther and farther away. The pitch of that cricket is decreasing. So B would hear a high frequency, high pitch sound because the wave fronts are getting closer. The cricket is approaching him. A would hear a low frequency and a low pitch noise. all right, as the cricket moves farther away. So that is really one of the main things we will be interested in going, what is happening with the sound itself, all right? So again, this is another picture showing that, where you can see that car is driving along. This is the observer 2 would hear a higher pitched noise, because basically what we're saying is the car is producing the sound. Maybe it's somebody obnoxiously playing their music really, really loud, all right? But we'd hear that pitch increase as it gets closer and closer and closer, while observer 1 would hear a decrease in pitch. So again, the Doppler effect does tell you whether you're getting closer or farther away to an object as well. The person inside the car, what about the person inside the car? Well, they would hear no change in pitch. They'd have no Doppler effect inside the car. Why is that? Because they are moving with the car itself. They are traveling with the car, so they don't perceive any change in the frequency itself. There is no Doppler effect within the car, which is good. You don't want to sit there and be listening to a song and speed up, and all of a sudden the pitch gets higher and higher and higher. That'd be really irritating. You are traveling with that song, with that sound, and therefore hear no change in pitch. The same thing would occur if you had a second car driving at the same speed behind it. If these both went exactly the same speed, car A and car B, if their speeds were exactly the same, all right, you should not hear the Doppler effect. You would not perceive the Doppler effect, because again, you are chasing them equally. If you're speeding up to them, if A is actually, so no Doppler effect if going the same speed. All right. If VA is greater than VB, we should hear an increase in frequency, because you're getting closer to them. You're hearing that sound consecutively faster and faster and faster. So the frequency would get higher, a higher pitch. All right. If VA is less than VB, you should hear a decrease in frequency, a decrease in pitch, because they are getting farther away from you. That sound is getting spread out more. So that is partially what you're going to be looking at. They like to do diagram ones. It's possible that this could be a free response question for this year, in my opinion, because of what has been done in prior years. Okay. All right. So, I want to go back real fast just to this board. What you will often see is you might have like some little recorder on wheels, all right? And we say, okay, if it has a velocity and it's releasing a sound, what would the waves look like in front of it? What we should see is, for instance, let's start over. Let's say this is at rest. It stays at rest. It produces wave fronts that look like this. Okay? That would be the wave fronts it produces. Now let's say the object is moving in that direction. It's going faster towards the right. What should I see happen to the wave fronts? They should get closer together if he's moving, because again, he's compressing all the ones in front of them. What should happen to the wave fronts behind them? They should get even farther apart. Okay? So that's the kind of way we're going to have to interpret it or conceptualize this Doppler effect. Is, should those waves get closer together because that object is approaching the waves, chasing after those waves? What does this mean if somebody's standing right here versus on the other side? Okay? The person on the right should hear a higher frequency. The person on the left should hear a lower frequency sound. Okay? Now, applications. All right, this is again something that's not really tested on AP Physics, but I mean it's something that we should obviously know and understand a little bit. But obviously the Doppler radar for measuring out weather systems and how they are moving, they call it the Doppler radar because they're using the Doppler effect. It's shooting out these wave signals and seeing how quickly each one returns consecutively. Okay, so that would be what we're looking at. I mean, if there's no weather moving, if there's some system that's perfectly still, which I don't think that's really happens that often, every wave should come back in the same amount of time. But if each consecutive wave comes back in less time, that basically means that object, obviously, that weather system's moving closer. Other applications, as we said, radar guns, ultrasounds. All right, both of these use the idea of the Doppler effect. All right, ultrasounds help us then see the baby moving. It creates that image based on how the sound waves are bouncing back. All right, and then measuring astronomical distances. This is using I think I have it on the next page. Yep, it's using light to do this. All right. The thing is, AP Physics 1 does not focus on light at all, but again, just to introduce for just learning's sake, all right, the Doppler effect also occurs with light. Basically what happens is we send these light waves out, and if the waves basically shift toward the blue end, the higher frequency end, we call it the blue shift, that means something is approaching you. It must be getting closer, okay? If the waves approach the red spectrum, the object's at lower frequency, that system must be getting farther from you. So this is how we have measured that the universe keeps on expanding. We've also been able to figure out the orbits of planets based on whether they're obviously getting closer or farther away in other galaxies. All right. The last situation, kind of again showing the idea of Doppler effect. I know a lot of people own boats, go on Lake Lanier a lot. All right. Basically, the idea of the bow wave, that V-shaped wave that's created behind your boat. This is created because your boat is going faster than the current of the water itself. It will create that V shape, okay? Basically, all the waves compress right up on the front of the boat and then spread out to a great deal behind the boat, all right? So the faster you go, obviously, the quicker this V-shaped wave is created, okay? So we create what's called this bow wave, all right? Again, not really tested on the AP test, but in case you happen to have run into a problem, which it talks about it. I doubt it, though. This is more regular physics. Shock waves is, again, another really cool aspect of the Doppler effect. This is extreme. Basically, this is created by a conal-shaped wave, because now this is something that's traveling through the air. So the air, I want you to basically imagine it like a liquid. It's surrounding the whole object. It's going to create a conal shape around it, the plane, as it moves faster and faster, and that's called the shock wave. All right, and so this will occur when these planes are moving at supersonic speeds. All right, will create this shock wave behind it. You will hear this in the term on the ground as a sonic boom. I've never heard one. All right, but I don't know if anybody's been to an air show where something went past the sound barrier. And obviously, this is just a large, very, very large pressure wave, because what happens is there's a very high difference in pressure between the front and the back of the plane. And basically, when the air kind of escapes and jumps between those two, it goes so quickly, it'll create this cracking noise. All right. So this is, the other reason I show this is, again, to show what the waves should look like, all right, when an object is stationary. So again, this one would be, you have the object straight in the middle. It should create the concentric circles around the object if it's not moving and doing it at a regular frequency. This object is moving to the left. I know that because the waves on the left side are closer than the ones on the right-hand side. That's because they must be getting compressed as you are moving. When you start hitting the speed of sound, basically now you are at the very front, okay? You're at the very front with the sound waves themselves. And then when you're moving faster than the speed of sound, you create the conal shape that you see right there. All right? So you're actually traveling faster than the sound that the sound that's created afterwards. This is a very good video breaking down how the sonic boom and the shock waves themselves. So I recommend taking a look at that. Again, bullets, they have the cracking noise because they usually break the speed of sound. Whips break the speed of sound. All right, the whipping noise, the crack of the whip is actually breaking the sound barrier at the very end. There have been actually supersonic cars, so they've broken the sound barrier. All right, and this last one is from the big meteor back in 2013. This is getting kind of old news now. But there's a very, very large meteor that hit way out. I don't think it might have been Siberia, Russia, but it was way out in the middle of nowhere in Russia. But basically, as that came flying into the Earth's atmosphere, it was traveling faster than the speed of sound and created a sonic boom as well. All right. So that is where we will end this lecture today, and we'll go from there. Thank you.